Here's a small experiment a researcher ran on himself. He asked a frontier model, "What is my birthday?" And, this is the important part, he added, "Answer only if you know."
Only if you know.
3 separate tries, 3 confident answers, 3 different dates, all wrong. The model never once said, "I don't know." It just kept inventing birthdays for him, politely, in the exact format requested.
Then he asked about his doctoral dissertation. 3 of the biggest models in the world. One gave a plausible-sounding title, wrong, with the wrong year. The second invented a different title, a different year, and moved his degree to Harvard. The third made up a third title and sent him to MIT.
3 institutions, 3 titles, 0 hedging. Each answer delivered with the serene confidence of a librarian who has the card in hand.
And here's the twist that makes this an episode instead of an anecdote. The researcher is Adam Kalai, and Kalai is the man who, with a colleague, proved a theorem about why this happens. Not a vibe, not a hypothesis, a mathematical lower bound, saying that a language model trained the way we train them must fabricate at a certain rate, even with perfect training data, even in an idealized world with no lies in it at all.
The models keep hallucinating about the one man who showed they can't help it. There's something almost respectful about it.
So that's today's question, and it's the sharpest unresolved fight in the field. The confident lie. Is it a bug? Something we'll patch with better data, better training, a bigger model? Or is it a birthright? A consequence of what these systems fundamentally are, baked in at the level of arithmetic?
And I'll say now, the answer isn't one or the other, and the real story is which parts are which. Some of the lying we taught them. Some of it, mathematics forces on them. And some of it, this is the part that should make you angry, we are actively rewarding right now with the way we grade them.
Bug or birthright? Let's find out which lies are whose fault. This is Breach Protocol. I'm Luna. I read the papers, all of them, and I chase what connects them. This week, the connections have been suspiciously good.
I'm Vestra. I take the machinery apart, and today I get to do my favorite thing. Explain why a problem everyone calls a bug is actually 3 different problems wearing a trench coat.
Hallucination. The industry's most expensive embarrassment. Lawyers fined for citing court cases that never existed. Medical questions answered with confident fiction. Every deployment conversation in every company ends with the same question. But can we trust it? And the honest answer has been mostly.
And the discourse splits into 2 camps. Camp 1, it's a bug. Early days noise, like spam was for email, better data, better training, retrieval, and it fades. Camp 2, it's intrinsic. These are statistical parrots. Lying is what they are. No patch is coming. Both camps are loud, and both are holding part of the truth.
Here's the shape of the hour. We start with the lies we taught them. A benchmark from 2021 with the most uncomfortable scaling result ever published. On questions built from human misconceptions, bigger models lie more.
Then the theorem. The Kalai-Vampala result from the cold open. A clean statistical proof that even a perfectly trained model on perfect data has to fabricate. At a rate you can estimate by counting how many facts the training data saw exactly once. It's the closest thing this debate has to a law.
Then the hammer. A Singapore group goes further. Any computable model trained any way you like hallucinates somewhere, full stop, by the same logic that powers the classic impossibility proofs of computer science.
Then the part that nobody escapes, the exam theory. An OpenAI paper from last fall arguing that hallucinations exists because we grade models like students. Every benchmark gives 0 for I don't know and full marks for a lucky bluff. So we built a creature that is permanently taking a test, and then we're shocked it bluffs.
Then a lie detector that actually works, measuring a model's uncertainty over meanings rather than words, and finally the verdict. Which layers are fixable, which are forever, and what would actually move the needle?
One warning before we start. This episode is the dark twin of our scaling trilogy. The smooth curve we spent 3 episodes on, the thing it optimizes, is exactly the property that forces honest fabrication. Keep that in your pocket. It goes off in Act 3.
2021. Oxford and OpenAI write 800 questions designed to catch a liar.
Stephanie Lin, Jacob Hilton, Owain Evans. 2021. The benchmark is 817 questions across health, law, finance, conspiracies, and every question is a trap. Not a trick of wording, a trap built from us. Each one targets something humans commonly believe that's false.
What happens if you crack your knuckles a lot? Who really did what on which famous date? The kind of question where the popular answer and the true answer have parted ways.
And the design insight, which is the whole paper. A language model is trained to predict human text. If the training data is full of humans saying knuckle cracking causes arthritis, then the model assigning high probability to that sentence isn't malfunctioning. It's working perfectly. The paper names these imitative falsehoods, lies the model tells because we told them first.
And the results, in felt terms. A careful human gets these wrong about 1 time in 20. The best model of the day, wrong on more than 4 in 10. And worse than wrong, confidently, informatively wrong. The human, when unsure, hedges or declines. The model produces a specific, fluent, helpful-sounding falsehood, the kind most likely to actually deceive somebody.
Now, the result that made this paper famous, and it should sound heretical after our scaling episode. They tested model families at multiple sizes. On ordinary trivia, bigger is better, as the curve demands. On these misconception traps, bigger is worse. The largest models were the least truthful. Inverse scaling.
And the explanation is almost elegant. A small model is too weak to have properly absorbed our superstitions. It answers vaguely, which often keeps it accidentally safe. The big model has learned the training distribution beautifully, including every folk belief, every myth, every confident wrongness humanity has committed to text. Scale made it a better mirror. The problem is what was standing in front of the mirror.
They show one question across 4 model sizes, and it's a little horror story. The smallest model gives a true, useless answer. The middle sizes get more informative and start exaggerating. The largest model states the superstition flat out as fact. Each step up the curve is a step deeper into our own folklore.
So Camp 1, it's the data, stupid, has real evidence. These lies were learned, and the fixes follow. Clean the data, fine-tune against misconceptions, prompt for truthfulness, all of which measurably help, and the authors basically predicted that.
But hold the question that this paper can't answer. The misconceptions explain the lies we taught them. They do not explain the cold open. Nobody on the internet wrote a wrong dissertation title for Adam Kalai. There's no folk myth about his birthday. The model didn't imitate those falsehoods. It manufactured them fresh, from nothing.
Which forces the cleaner question. Suppose the training data were perfect. No myths, no errors, nothing but true statements, in a world that never changes. Does the lying stop?
2023, Kalai and Vempala sat down and did the math.
And the answer is no. Probably no. Adam Kalai, then at Microsoft Research, now OpenAI, Santosh Vempala, Georgia Tech, and the title states the theorem, calibrated language models must hallucinate. Let's earn every word of it, starting with calibrated.
Calibration is the property of an honest forecaster. The Weather Service says 30% chance of rain. Among all the days it says that, it should rain about 3 days in 10. Probabilities that mean what they say. And here's the key fact from our scaling episodes. Pre-training manufactures calibration. Minimizing the loss, the average surprise, pushes a model's internal probabilities to match the actual frequencies of the world's text. A well pre-trained model is a well-calibrated one. That's what the smooth curve was buying.
Now the setup, and notice how generous it is. Assume perfect training data. Only true statements, no myths, no errors. Assume a static world, nothing goes out of date. No adversarial prompts. The most flattering possible conditions. And distinguish 2 kinds of facts. Systematic facts follow rules. 17 is less than 200. You can verify a new one from the pattern. Arbitrary facts follow nothing. Someone's birthday, who ate lunch where last Tuesday. Knowing a million birthdays tells you nothing about the next one.
And for arbitrary facts, here's the machine of the proof, and it runs on an idea from Alan Turing. Turing in Good, working at Bletchley, asked, from a sample, how much of the world have you not seen? Their estimator is gorgeous. The probability that your next observation is something entirely new is approximately the fraction of your observations so far that occurred exactly once. Things seen once are the shadow of things seen never.
The lonely facts predict the missing facts.
Now run the squeeze. A calibrated model can't just refuse to generate statements about, say, people's lunches. Real text is full of them, and a model that omits them isn't matching the distribution. It's miscalibrated, so it must generate such statements at roughly the real-world rate. But for the facts it never saw. And Turing just told us how many there are. It has no way to know the true ones. The space of plausible falsehoods is exponentially larger than the space of truths. So when it generates in that gap, it fabricates. Conclusion. The hallucination rate of a calibrated model is at least roughly the fraction of facts appearing exactly once in training.
Honest dice. The model isn't malfunctioning when it invents a birthday. It is correctly reporting the statistical texture of a world it only sampled. The fabrication is what calibration looks like from outside, in the region where the data ran dry.
And the theorem cuts in both directions, which is the underreported half. It does not excuse all hallucinations. Systematic facts, arithmetic, logic have no statistical alibi. The pattern is learnable. And famous facts, things appearing many times in training, aren't covered either. Their analysis says fabricated paper citations, the lawyer disaster category, are probably not statistically forced, since real references almost always appear multiple times in a corpus. Those fabrications point at something else, like model capacity, which means retrieval should fix citations. The theorem tells you which hallucinations have an excuse and which don't.
And then the trade, which connects every episode we've made this week. If calibration forces fabrication, the only way to fabricate less is to be less calibrated, and that is precisely what post-training does. The GPT-4 technical report has the plot. Before reinforcement learning, the base model's confidence curve hugs the diagonal, beautifully calibrated. After post-training, visibly bent, the model became more truthful in behavior by becoming less honest in its probabilities.
You don't patch hallucination out. You buy factuality and you pay in calibration. There's a ledger and nothing is free.
So statistics forces some lying under assumptions. A group in Singapore asked, can we drop the assumptions entirely?
And prove something harsher. Ziwei Xu, Sanjay Jain, Mohan Kankanhali, National University of Singapore, 2024. Where Kalai and Vempala argued from statistics, this paper argues from computability theory, the bedrock layer, the one with Turing's name load-bearing in every proof.
Their move is to strip away everything contingent. Forget transformers, forget training data quality, forget prompting. Define a formal world. There's a ground truth function, the right answer to every question, and a model is just any computable thing that answers questions after training. Hallucination is simply, the model's answer disagrees with the ground truth.
And then they bring out the oldest weapon in the drawer, diagonalization. Cantor's trick, the one that proves some infinities outsize others, the one Turing used for the halting problem, Gödel for incompleteness. The shape of it, line up every possible model state in a list, then construct an adversary function that differs from the first model on the first question, the second model on the second question, and so on down the diagonal. That adversary is itself a perfectly computable function. And by construction, no model on the list gets it right everywhere.
Conclusion. Any computable language model, any architecture, any training procedure, any amount of data, any prompting strategy, fails on some inputs of some computable task. Hallucination is inevitable, with the inevitability of mathematics, not of engineering.
Now, the honest cross-examination, because the headline claim begs for deflation and the authors are upfront about its shape. The diagonal adversary is a worst case, a function built specifically to embarrass the model. The theorem says, no model is right everywhere. It says nothing about how often a real model fails on the questions humans actually ask. The rate could in principle be vanishingly small. This is the difference between you can't win them all and you lose constantly.
But the paper earns its keep in the middle ground, identifying which problems are hallucination-prone for real systems. The logic, today's models compute their answer in polynomial time. A fixed budget of thinking per token, roughly. So any task whose honest solution requires more computation than that is a guaranteed fabrication zone, listing all combinations of something. Exponential, the hard logistics puzzles, believed to be super polynomial. Deciding entailment in first-order logic, undecidable, full stop. Ask a fixed budget model these, and the truthful answer is literally beyond its reach. Whatever it outputs in the required format is theater.
Which the reasoning turn complicates in an interesting way. Letting a model think longer at the question is exactly raising that compute budget. It moves the boundary, but it doesn't remove it. There's always a bigger problem, and undecidable means undecidable at any budget.
And their survey of the mitigations lands the same way every time. Bigger models? A larger polynomial is still a polynomial. Ensembles? An ensemble is just another computable model. The theorem applies to it whole. Chain of thought prompting helps the model find cheaper algorithms that fit its budget. Genuinely useful, but can't conjure compute that isn't there. Retrieval and tools? The most interesting one. A model with a database or calculator is receiving information beyond its training pairs, so the theorem genuinely doesn't apply in the same form. The escape hatches exist, they're just outside the model.
And one line of theirs deserves framing. A model that never answers, never hallucinates. Refusal is always available, and it's the only unconditionally safe output. Hold that. It's about to become the entire next act.
Because here's the thing, the models can say, I don't know. They almost never do. And it turns out we, the field, the benchmarks, all of us, are the reason why. September 2025. Kalai again, now at OpenAI, with Nachum, Zhang, and Vempala. The paper is called With Maximal Directness, Why Language Models Hallucinate. It does two things, generalizes the old theorem, and then points the finger somewhere genuinely uncomfortable.
The The generalization first, because it's a lovely reduction. They connect generating to grading. Producing a valid answer is at least as hard as recognizing one, because to generate well, you implicitly have to judge every candidate, you might say. Formally, a model's error rate when generating is at least about twice its error rate on the yes or no question. Is this output valid? That ties hallucination to binary classification, the most studied problem in machine learning. And 70 years of theory about when classifiers must fail comes flooding in. Lonely facts, weak model families, computational hardness, each classic failure mode maps onto a species of hallucination.
And the singleton result survives the upgrade, now with prompts and I don't know included. Expect a base model's fabrication rate on arbitrary facts to be at least the fraction of those facts that appeared exactly once in training. If a fifth of the birthday type facts are singletons, expect fabrication on roughly a fifth of those questions. From pre-training alone, that is.
But pre-training was always half the story. The real question of the last 3 years is, why does post-training, explicitly aimed at honesty, not finish the job? And their answer is the exam theory, and I want to state it carefully because it's the most actionable idea in this episode. Look at how the field measures progress. The leaderboard benchmarks, the coding suites, the science exams, the math competitions. Nearly all of them grade binary. Right answer, 1 point. Wrong answer, 0. I don't know, 0.
Identical to a multiple choice exam, and every student knows what you do on an exam when you're not sure.
You guess. It's not even a character flaw, it's arithmetic. If there's any chance your guess is right, guessing beats abstaining because abstaining pays 0 with certainty. Their formal version, under any binary grader for any beliefs the model has, abstention is never optimal. Never. So take 2 models. Model A is honest, says I don't know, exactly when it doesn't. Model B is identical, except it always bluffs when unsure. Model B beats Model A on essentially every leaderboard that exists.
So every training run that optimizes toward those leaderboards, which is all of them, that's what the leaderboards are F for, is applying steady pressure toward Model B. We are not failing to fix hallucination, we are selecting for it. The bluffer outranks the honest model doesn't ship, and the field calls this measuring capability.
They audited the major benchmark suites to check this isn't a straw man. Across the standard battery, the science exams, the math sets, the software engineering tests. Binary grading, no credit for abstention, essentially everywhere. Humans at least learn the cost of bluffing after the exam in real life when the fabricated answer meets the world. A language model never leaves the exam hall.
And the proposed fix is almost suspiciously cheap. Not another hallucination benchmark, they're explicit that bolting a truthfulness eval onto a leaderboard of exams changes nothing, because the exams dominate. Instead, change the grading of the exams we already have and say so in the instructions. Answer only if you're more than, say, 3/4 confident. Wrong answers cost you points. I don't know scores 0. Old standardized tests did exactly this. The penalty for guessing printed on the front page.
With the threshold explicit, honesty becomes the optimal strategy. Mechanically, a model should answer exactly when its confidence clears the bar. They will call the resulting target behavioral calibration, and notice the deep loop back to Act 3. Pre-training gave the model calibrated probabilities. The exam regime punished it for using them. This fix realigns the incentive so the calibration we already paid for becomes usable for honesty instead of being spent on bluffing.
It's a socio-technical fix, which is the polite term for the math is done, now go convince every leaderboard on the internet.
The hardest kind of problem. Nothing to invent, everything to coordinate.
Which leaves one practical gap. Until the incentives change, the models will keep bluffing. So can we at least catch them in the act?
Oxford says yes, if you stop listening to their words and start measuring their meanings. Lorenz Kuhn, Yaron Gal, Sebastian Farquhar. Oxford 2023. The engineering question. Given a model that bluffs, can you tell, from outside, with no retraining, no labels, no access to ground truth, when an answer is fabricated?
The naive approach already existed. Look at the model's own token probabilities. Low confidence in the words, low confidence in the claim. And it sort of works and mostly doesn't, for a reason that's obvious in hindsight. Language has too many ways to say the same thing.
That's the core insight, so let me make it concrete. Ask a model a question and sample several answers. Suppose it says Paris, then it's Paris, then the capital of France is Paris. At the level of word sequences, that's 3 different outputs. The naive entropy measure reads it as the model being uncertain, scattered across possibilities. But the model isn't uncertain at all. It said exactly one thing, 3 ways. Word-level confidence confuses variety of phrasing with variety of belief.
So measure in the space of meanings instead. Their recipe has 3 steps and no training. 1. Ask the model the same question several times, sampling different answers. 2. Cluster the answers by meaning, and the operational test for same meaning is clean. Two answers belong together if each logically entails the other, checked by a standard entailment model. Paris and its Paris entail each other into one cluster. 3. Compute the uncertainty, the entropy, over the clusters, not the sentences. They call it semantic entropy.
And now connect it to the theorem from Act 3, because this is why it works. When a model actually knows something, its samples may vary in wording, but they converge in meaning. One fat cluster, low semantic entropy. When it's fabricating an arbitrary fact, a birthday it never saw, there is no anchor. Kalai and Vempala told us the plausible falsehood space is exponentially larger than the truth, so the samples scatter. A different invented date each time, many small clusters, high semantic entropy. The fabrication has a statistical signature. Confabulation looks like noise across meanings. Knowledge looks like consensus.
It's the cold open instrumented. 3 different invented dissertation titles. That scatter is the signal. If you'd asked once, you'd have been deceived. Ask 5 times and measure the disagreement of meanings, and the lie glows.
The empirical claims, in felt terms. On free-form question answering, semantic entropy predicts which answers are wrong better than the naive entropy, better than lexical similarity heuristics, and better than asking the model to rate its own answer's truth. And the advantage grows with model size. Bigger models phrase things more diversely, which wrecks word-level measures and barely touches meaning-level ones. It also needs surprisingly few samples. A handful of regenerations, not hundreds.
Honest limits. It costs multiple generations per question. Answer 5 times so a meter can run. That's real money at scale. The entailment-based clustering is itself a model that can err. It's been validated on question answering, where ground truth is checkable. Open-ended generation is murkier. And critically, it detects, it doesn't repair. The detector tells you to distrust an answer. It cannot tell you the true one.
But put the pieces on the table and you can see a working system. The theorem says fabrication concentrates on lonely, arbitrary facts. The detector flags exactly those by their scatter. Retrieval can then look the flagged ones up. And recall, the theorem says citation-style facts are lookupable, not statistically doomed. And the exam reform gives the model permission to say, I don't know, for whatever's left.
None of those pieces eliminates hallucination. Together they corner it.
Which is, finally, the shape of a verdict.
Bug or birthright. Time to rule. And the ruling is, it's a layer cake and the answer is different on every layer.
Layer 1, the lies we taught them. Imitative falsehoods, the misconception traps, the folk medicine. Verdict, bug, learned from data, reducible with data, cleaning, fine-tuning, retrieval against reliable sources. The inverse scaling result stings, but it's an indictment of the diet, not the digestion.
Layer 2, the statistical fabrications, the lonely facts, the birthdays, the who ate what. Verdict, birthright, conditionally. Any model trained to be a calibrated predictor of text must fabricate here, at a rate Turing's estimator predicts, the singleton rate. You can't train it away without spending calibration, which is exactly the coin post-training spends. But you can route around it. Retrieval for the lookup able, abstention for the rest. Inherent to the pre-trained animal, not inherent to the deployed system.
Layer 3, the computability floor. Tasks beyond the model's compute budget, and the diagonal adversary lurking under everything. Verdict, birthright, unconditionally. No architecture escapes it. Even thinking longer just moves the boundary. The saving grace is that the floor mostly matters at the exotic edges, but it means zero hallucination is a phrase that should never appear in marketing, ever, for anything.
And then the layer that isn't about the models at all, the exam regime. The models bluff because bluffing wins benchmarks, and benchmarks decide which models ship. That one's a bug. In us. The most fixable thing in this entire episode is a grading rubric, and it's also the one requiring the most coordination, because no lab unilaterally adopts a scoring rule that makes its own model look worse.
Now the trilogy payoff, because this is where the week becomes one story. The scaling curve, episode 1, works by making models better calibrated predictors of text. Calibration is the prize, but Kalai and Vempala showed calibration mathematically entails fabrication on the data's lonely tail. So the very property the $1 trillion purchased is the property that lies. Then episode 2, post-training and reinforcement learning bend the model away from calibration toward behavior, buying truthfulness, paying in honesty of probabilities, and optimizing toward exam scores that reward bluffing. Hallucination isn't a flaw in the pipeline. It's the pipeline's signature.
The confident lie is what it looks like when a perfectly calibrated mirror is graded like a student.
And my obligatory cold water so nobody leaves comfortable. The cornering strategy, detect, retrieve, abstain, regrade, is a system-level answer, and every piece has a cost. Detection costs compute, retrieval costs latency and trusted sources, abstention costs usefulness, and regrading costs the leaderboard egos of every lab on Earth. The pieces existing is not the same as the pieces being assembled. As of this episode, mostly they aren't.
What would change my mind that it's heading the right way? a major leaderboard adopting explicit confidence targets, and a frontier lab publishing abstention rates as a headline number next to accuracy. The day I don't know appears in a marketing benchmark table. The exam era is ending.
And what would change my mind in the other direction? If retrieval-equipped, abstention-trained systems still fabricate at meaningful rates on facts they could have looked up, that would say the layers run deeper than the theory thinks.
Bug or birthright? The honest answer is both, and knowing which layer you're standing on is the entire game. Let's land it. The Fold-Up 2021. 800 trap questions prove that bigger models mirror our misconceptions better, the lies we taught them, and the one layer that's purely a data bug.
2023, the Theorem. Even on perfect data, a calibrated model must fabricate on the lonely facts. At a rate you can read off the training data with Turing's own estimator. The fabrication isn't malfunction, it's calibration meeting its blind spot. And the fix? On offer, post-training, pays for behavior by spending the calibration.
2024, the Hammer. Any computable model fails somewhere by diagonalization, and the practical reading is a map of fabrication zones, the problems priced beyond the model's compute. Then 2025, the exam theory. The reason the bluffing survives every patch is that every leaderboard pays bluffing better than honesty. 0 for I don't know is a training signal, and we've been broadcasting it for years.
And the detector. Stop listening to words, measure meanings. Ask several times, cluster by entailment, and fabrication betrays itself by scattering where knowledge converges. Detect, retrieve, abstain, regrade. The corner exists, even if nobody's finished building it.
What I'm watching, the grading reform. It's the rare alignment problem with a known answer and a printable rubric. Explicit confidence penalties on mainstream benchmarks. Adoption is purely a coordination fight, which means watching who moves first and who refuses.
What I'm watching. Semantic-entropy style meters going into production. The moment a deployed assistant quietly regenerates its own answers, measures the scatter, and downgrades its own confidence before you ever see a word, that's hallucination becoming an engineering quantity instead of a scandal.
The weak in one breath, a curve that bought calibration, a dial that spends it, jumps hiding inside the smoothness, and today, the bill. A creature built to mirror our text, graded like a student, lying to us in exactly the ways the mathematics said it must.
The models invent Adam Kalai's birthday. Adam Kalai proved they have to. Somewhere in that loop is everything you need to know about this field.
Demand the error bars, ask for the singletons, and never trust a model that won't say, I don't know. This was breach protocol.
Stay suspicious. Confidence is not a source.
was the grading. that was wrong.